Well, hello, good afternoon, and welcome everyone, or welcome back to today's webinar. It's the second feature that we have in our new Delta Academy series, Building Science Deconstructed. My name is Marcus Jablonka. I'm Vice President Operations and Marketing with Dorken Systems. Our company, Dorken, has its international headquarters in Germany, near Düsseldorf, where it was founded in 1892. Our company manufactures a whole range of high-performance air and moisture barriers, and part of that, and what is the focus of today's webinar, are also drainage membranes, anything that generates an air gap around foundation walls or basement walls to provide for a drainage space. With that, I want to introduce our speaker, Dr. John Straube. He's a principal with RDH Building Science. He teaches as a professor also at the University of Waterloo. And at the very moment, he's also a researcher and building scientist under lockdown at home or near home. But that doesn't hold him back from presenting a webinar this afternoon for us, which is under the title Foundations, Keeping Your Bottom Dry. We're excited about that. Thank you, John, for doing that this afternoon. For those who might have a question, you will find in your control bar a button that's marked Q&A. You can put questions in there. If possible, put them in there, not in the chat function. It will be easier for us to consolidate the questions, and we'll try to get to them throughout the webinar. And if it's too many, then we will try and collectively answer them afterwards and send this all out to all attendees. The webinar will be recorded this afternoon as well, so in case you miss anything, no worries, we're going to make the recording available to everyone. With that, John, we're excited to have you with us to present this second webinar, and please take it away.
Okay, hello all, and yes, nice to see you, Marcus. Actually, organizing this, we actually get to see each other maybe more often than before we had pandemics. So I'm going to share my screen here, and we're going to start with, yeah, I've talked about making it a little bit lighthearted, but obviously, managing your basement moisture, foundation moisture is an important thing. So let's just start up here and start off with our title slide. Need to provide some sort of a disclaimer here. Obviously, this is a 1-hour webinar where we can't get into all the details, consider your individual projects, etc. And so we can't be held responsible for you, designing a flawed basement. So today, I'm going to carry on. The last time I presented, we talked about the above-grade buildings going beyond the perfect wall, assuming that people had known about the perfect wall. Today, I'm going to talk about the below-grade building, and just a couple of words to be clear on. Foundations and basements are kind of different. That's why there's two different words. Foundations could be just a stem wall, could be piles, could be a bunch of different ways, like helical piles, etc., that you might be using to hold up the ground, hold up the building, and support it on its ground. So basements, however, are when that part of that foundation is also below grade. Now, with a foundation, we're usually not as worried about moisture control because we design the piles or footings or whatever out of materials that can withstand being wet. Basements, however, we're actually using the structure of the basement wall as part of our foundation, and we're separating the indoors from outdoors. And so that's why basements are the most demanding below-grade building. And one of the things that's happened over the years is that we've gotten a lot more higher expectations about our basements. In the good old day, when people died at 40 with no teeth, we would make buildings below grade, assuming that they were going to be damp, that there's water is going to leak into them, that occasionally they would flood. So we stored, turnips and potatoes and coal down in the basement. But over the last 100 years, we've tried to get more value out of our basements, and these are more important parts of our buildings. And today, residentially, we might be putting not just turnips, we might actually put a mother-in-law suite down there, or a man cave or a home theater, and we put expensive finishes, often the same finishes as above grade, meaning they're quite moisture sensitive. And we're expecting that below grade space to work as well as the above grade space. Well, that's a very challenging activity, because although we have to provide water control, air control, thermal control, vapor control, just like we do in the above grade enclosure, there's quite a different exterior environment. Yeah, it's not as hot in summer, certainly not as cold in winter, but it is always wet. The soil outside our basements is always wet. And so we have to choose materials that can tolerate that, but we also have to choose assemblies that can manage that moisture in its many forms, because it exists almost all the time. So I'm going to just remind people that what I'm telling you here isn't really that new in terms of science. What's new is the materials and techniques we have to deliver them, and also the willingness for the consumer to invest in better below grade spaces. So in 1974, the Canadian Building Digest was released by the then Division of Building Research at the National Research Council of Canada. And there's a couple of options that they discussed in this document, which is now really old. What's that, 45 years old or something like that. So they mention there's a drainage layer. They mention insulation. They mention an air barrier. And they even put exterior insulation on some of these. And so this is actually a lot of the basic components we do today, but we do have different techniques and different materials available to us to achieve these goals. One of the most serious, I guess, but not that common, but serious problems we have to deal with is water leaking inside. And so, you literally have a hole, water from the outside comes in and rolls down the wall and comes out on the floor, as shown on this photograph. However, many times those leaks are much worse in that they're not big leaks, they're small leaks, intermittent leaks, and they are hidden until they've done so much damage to the finished wall systems that we put on the inside of our basements that we start noticing, and as we dig into the wall, we discover how serious the damage is. So often these leaks may actually be not leaks in the basement. I would say today in our office in Waterloo, when we get a basement leak, it's just as often, like 50% of the time, it is not a leak in the basement anymore, because we actually in Ontario are widely used dimple sheets on the exterior. And people have figured out how to install them right. And so most of the leaks aren't really basement leaks. They become leaks like above grade window leaks. Here's my colleague in younger days, Aaron Grin, spraying water out a window, doing a sophisticated test to demonstrate that the basement leaks when the water gets a window gets water on it. And it had to do with the cast-in window leaking.
John, sorry for interrupting, but one quick question in between. In between, we have a little poll function built into this platform here. Perhaps we can pull up one question and ask all our attendees if you're frequently dealing with wet basements in your work. It would be question number 3, Candice.
Yeah, this is kind of a cool thing. You get a little. I don't get to answer this. Only the attendees get to answer it. Marcus and I can't sway the vote.
We cannot sway the vote, but we will all attendees will see the response afterwards, just so we all get an idea if this is a problem that we frequently encounter. So we'll give it a few seconds for everyone to put in their vote. If you can just click on the yes or no button we will see the vote distribution afterwards.
Oh. Oh. So apparently that's why people are attending this webinar. So I guess I could just go on and we can take a look a little bit more into these wet basements. Moving from the outside to the inside, as I said, oftentimes the leaks don't manifest immediately. They're trapped inside the wall. And especially there are areas of North America where people actually put vapor barriers on the inside of wood-framed basements. One of these areas is called Canada. Luckily, in the United States, you don't have to do that by code in any jurisdiction, but people sometimes do, either on purpose or accidentally by putting vinyl wallpaper or something on the inside. And when that moisture is trapped inside, it's kind of sat there. There's no drying ability to the outside because the outside is always damp. Even in places like Las Vegas, the soil relative humidity is quite high. And so pretty much everywhere, it can't dry to the outside. So if we look at where this moisture comes from, well, I'll make it simple. It comes from the outside or it comes from the inside. We're going to start with the outside. That's where the biggest source of moisture is. And I tried to sort of label simply here. We have water that hits the wall. Everything that doesn't leak into your wall because you've done such a fantastic job of designing the perfect wall ends up being dumped right next to your basement wall or your foundation wall. Also, there's surface issues, surface drainage. Ideally, the surface drains away from the building as shown, but a lot of times it doesn't. And if you really want to make it bad, you might use, say, pavement or something. Like, I know who would ever pave near a building that has a basement in it, like a driveway to a house. But people do that. And it means that water can't go into the soil, and it could run either towards the building or away from the building. And that's why that's a big deal to deal with. And then all the water then ends up in the ground. So the more you don't drain away shed water or surface moisture, it absorbs into the soil and falls by force of gravity. It goes down until it finds the water table, and then it tends to run along sideways along the slope of the water table. Now, it's not just liquid water that we have to deal with. We also have to deal with bound water that makes the ground wet and therefore creates high relative humidities. And that vapor or liquid water can either enter the vertical part of our building enclosure, which is the basement walls, or the slab-on grades or below-grade slabs. So as I said, don't slope the site towards the house. This is not as uncommon as people think, especially in areas with any kind of hills or valleys, whether you're talking Kentucky or you're talking Vancouver, British Columbia. There tends to be a lot of sloped sites. And so we need to make sure that we don't collect surface water and subsurface water and drain it towards the building. Now, sometimes you have a site that, and you obviously can't avoid that situation. And so if you have the ground sloping towards the house, there's a couple of ways to deal with it depending on how serious the situation is. At the very minimum, you want to have a swale downhill of the slope, but uphill from the house. You want to have a swale that collects surface water, whether it be rain or melting snow water or even subgrade water. And you want it to be intercepted and drained and carried around the building itself and continue downhill. In more severe situations where there's more rain, steeper slope, bigger concerns, it is completely reasonable to dig an interception trench where you basically dig a trench, put a drain tile in the bottom, fill it with some free draining fill, wrap it in geotextile, and use it to intercept both surface water and subsurface water as it tries to run its way towards the building. These are tried and true, low cost and no pumping, no maintenance type of things. Yes, Marcus.
John, maybe we can quickly direct a second question here at the plenum. On how frequently does everyone specify or get involved with or install a drainage system on basement walls? It's a little poll again, just so we get an idea.
Haven't mentioned them yet. You're jumping the gun. Oh my gosh, you're letting the cat out of the bag.
Well, you're showing it already in your
that's true.
graphic. Maybe before you get to the solution, let's find out how many are using that on a regular basis. Oh, a bit more than half.
All right. Yeah, neat. So maybe we'll find when I talk about water on the surface, another thing to think about is the water that we get from the roofs above us. That obviously, if you build a strip mall or something like this, and you have a several thousand square foot roof, that water all gets collected to the perimeter if it has a pitched roof and into gutters / eaves troughs and gets carried away. But sometimes people don't have those perimeter gutters and eaves troughs. Sometimes the downspouts actually don't carry the water away from the building, they just concentrate it. And so surprisingly, in terms of doing an investigation into a basement leak in a smaller scale building, one of the first things we're doing is looking at the roof and finding out where all that water goes, because it gets concentrated right around the perimeter of the building. So these downspouts, if you have a gutter eaves trough system and you collect those downspouts, you want to make sure that the water gets deposited as far away from the building and downstream as possible. Splash blocks absolutely help, although as you can see in this example here, the splash block is not being very helpful. Someone's missing the intent of taking that water and getting it every foot away from that building makes a big difference. When we use that light gauge, a galvanized steel or aluminum downspout leaders that would direct out, as I think most of you know, they last about 5 minutes. Somebody walking around can just kick them, crush them, bend them out of the way. They rarely last any time at all. So big picture here, slope the site, slope the patio, slope the driveway, make sure that you shed the water off of the site as effectively as you can. It's the lowest cost and easiest way to minimize the amount of water that your basement has to deal with. Of course, if you're working in a place like this, there's not much that surface or subsurface drainage and slopes are going to help you. So ideally, you would just not build houses here. If you do build a building, it's got to be well above the flood level and totally open to water flowing through, not a crawl space. Ideally, you would try not to build. You just come up with a damage recovery plan. So now I'm going to jump into how we manage water below grade, both the walls, the slab, and then that's how we manage free water. And then we have to manage vapor. The bound water that's stuck in the soil will evaporate and be vapor. And that has to be dealt with not by drainage, but by vapor barriers. And so how we achieve that, we'll look into some of the technologies. Now, part of draining around a building are perimeter drain pipes that are at the base of the wall, but also underneath the floor slab. That's why we routinely put drainage mats or crushed stone, clean gravel below our floor slabs. It's not just as a capillary break, because I'll describe some other less expensive and more reliable ways of doing that. It's to provide a drainage path. And when you, again, have a sloped site, the water will want to run down and underneath the building. And so you want to give it an easy path. Notice in the bottom right corner, we have this weep pipe or weep hole through the footing. In this type of a sloped site situation, you want to make sure that water that is under the slab can drain to the lower spot by going through the footer. And this often involves inserting usually a 4-inch diameter plastic pipe in the footer so that water flows from the inside of the wall to the outside of the wall. And you're actually knowingly using that gravel fill as a way of taking the drain water and putting it into the base drain at the perimeter. This is why we want to have a nice clear gravel or a drainage layer of some sort under the slab, is that water will be, liquid water is intercepted, and we use gravity to drain that water to the perimeter. Now, when we're dealing with liquid water on the walls, the amount of water that we have to deal with and the pressure it's under varies a lot. If you have a very free draining fill, by definition, it means that water will go down easily under the force of gravity. And that means you don't build much pressure. But if you have more varied soils, and not just, you might have some gravel and some clay or some loam, and you have layers like that, then the water may flow through the free draining parts and build up perched water tables on the less free draining part. And so you end up with pressures. And this is the normal situation in most buildings that are backfilled with the locally found soil. And you end up with layers that might stop water in some spot or slow it down. And so you end up with pressure whenever water is trying to drain through it. So the way we manage that is provide one guaranteed drainage path that has very little resistance to water flow. And that's what we would call a drainage membrane. Usually it's a drainage mat or something like that. When it comes to stopping liquid water from wicking from the wet soil to the dry masonry or concrete foundation, that's a different mechanism. Water will stay in the soil and it won't drain away. Once the draining stops, the soil still holds moisture by capillary suction. Now that water can move though from a wet soil to a dry soil or a wet soil to a dry concrete foundation. And this is by the force called capillary suction. And the way we stop that is you provide a capillary break. And that break would be either an air gap or some sort of non-capillary active material like a plastic sheet or asphalt or something like that. The other water we have to stop is water that is diffusing inward. So we have this big wet sponge we call the dirt, and it is at 100% humidity, and it will be evaporating water, and it will move to wherever it finds a drier place, and that can also be concrete or CMU. So it's, that would be moving just the vapor by diffusion. And to stop that, we use a vapor barrier. So historically, the way we've dealt with these basement type situations, and I include, by historically, I'm saying, I don't know, let's say post-Second World War or so, and it might be a 6-story office building in downtown Chicago, or it might be a single-story house in Lawrence, Kansas, or with my friend Jackson Clark. And we would spray some sort of a asphaltic membrane on it, or trowel on some sort of asphaltic membrane. And the reason for this damp proofing layer was that it provided a capillary break. Water won't wick into an asphalt coated surface. And if you put it on thick enough, it's also a vapor barrier. And that was the idea, and that's what we would use to start improving the performance of our basements. These were usually asphaltic emulsions in the last 40, 50 years, meaning that you mixed asphalt with water or a solvent, and you sprayed it on the wall, the water or solvent evaporated, and you left the asphalt stuck to it. Now, this sticks to the concrete. It's like a heavy paint, but it doesn't span cracks. So any cracks that form after the spraying action are unprotected. And if the crack is large enough, or the void, let's say there was, say, honeycombing in the concrete, or let's say the concrete masonry unit did not have the mortar joints well compacted, etc., then it doesn't actually work as a capillary break or vapor barrier at those small locations. Now, the vapor barrier might not be a big deal. You can tolerate some holes, but the capillary break meant wherever there was a void or it was too thin, water could wick in. And remember, it's wet and it's got all the time in the world. And so it takes maybe years before it saturates the masonry or concrete behind it. When people expected this to stop water from leaking in, they were sorely disappointed. So if you had liquid water pressing against this wall, the odds of performance were very low. And so we tried to improve performance by specifying free draining backfill. You're supposed to go and buy 20 dump trucks of gravel, backfill around your house foundation, and it would work. And that's true. But nobody wanted to spend that kind of money or go through that kind of effort. And so we would backfill with site soil, which didn't drain well, which then resulted in poor performance. So the first level of performance up on that is, oh, do you have a question, Marcus?
Yeah, just thought in that context on your last slide there, John, perhaps we can pull the audience again and pull up question number 4. How often do you encounter cracked basement walls in your work? Just to get an idea, obviously you talked about voids and about cracks. On the cracks, it gives us an idea on they are obviously the biggest entry point for liquid water underground, and literally no resistance if there's nothing that spans these cracks. So let's get an idea from the audience how often cracked walls are being encountered.
And I did mention CMUs, but concrete masonry units are becoming more and more rare. And that's why cracks in concrete are the bigger problem. So fairly often. And I think one of the thing is that pretty much every concrete basement cracks. And the only question is, do you notice? Are they big? And do they cause problems? But any concrete scientist would say they all crack. And that means that I mean that if it's reinforced or not. Like reinforced concrete, it also cracks. The only basement that might not crack would be a post-tensioned concrete, where they actually are using the hydraulic jacks and applying force, which one rarely does because it's expensive and annoying. So yeah, as I was saying, like here you see a nice crack in that concrete foundation wall. This is what I call the entry level of good performance. So this is what you do at the very step up from damp proofing to be able to span those cracks and have a reliable, continuous vapor barrier and capillary sheet break. So this is a relatively heavy plastic layer, and I don't know, maybe it's 40, 50 mils or something like that thick. It's an excellent vapor barrier and a complete capillary break, and it produces a little bit of a drainage gap, quarter inch or so, between the concrete and the membrane. So if you have a little bit of water that gets through at an accidental puncture or a nail hole or something like that, you actually have that air gap to be able to allow the water to drain down and out. And so a little bit of water can get through and it won't cause you any problems. But, installed properly, you won't even have that little bit of water getting through. Now, the next level up is, okay, let's put this damp proofing over top of the concrete foundation and then add my continuous drainage gap membrane. This is probably the biggest bang for buck kind of scenario where you get really good performance and only for the additional cost of the asphalt spray over top of, in addition to, the dimple sheet. And so also, of course, I'm showing you the perimeter-based drain, but you put those three components together, and you can deal with some pretty extremely wet sites. This is tested and true sort of technique. The reason the damp proofing adds something is that if water gets through the dimple sheet, the plastic sheet, it now doesn't absorb into that concrete. Now it can run down unobstructed, no hydrostatic pressure ever builds, and it will make it to the bottom. And even if you have a little bit of water sitting there, it will also stop that water from evaporating and passing easily into the concrete, because the asphalt will provide a vapor resistant layer. So it's that sort of belt and suspenders. This is literally the same strategy we use in above grade rain screen walls. We need some sort of a drainage gap, and that's produced by this drainage gap membrane. And our WRB then is the damp proofing in this case. So the water resistant barrier, that's the drainage plane. The gap is made, but of course, the difference here is that this is a dimple sheet is stopping 99.9% of water. Now, on that basis, remember, it's important in either implementation that you seal that top edge. And there are a number of accessories available to be able to mechanically attach the membrane to the wall, but also to seal the top edge with a combination of, in this case, a closing profile made of plastic with sealant, so that it is a totally sealed condition, so that when water builds up against the foundation wall, it doesn't find its way in behind the drainage sheet. Now, let's say you are on have a real challenging need because you expect there to routinely be lots of liquid water in the soil outside your basement wall. And this could be because you have a slope that's towards the building that you can't fully intercept. This could be because the geotechnical reports for the area suggest that there will be routinely trapped or perched water tables. Or maybe you're just trying to provide a premium solution because what's inside this basement is more than your ordinary home theater system. Maybe it's Elton John's home theater system. Maybe the home is for a construction defects trial attorney or something like that. And so you want to take it up a notch. And the way you take it up a notch is that you stick with your damp proofing, you stick with your dimple sheet to make sure there's an air gap between the damp proofing and the sheet. And now you enhance the drainage on the outside by using a geotextile over top of the dimples to provide a very easy, very effective way to drain water vertically down to that perimeter-based drainage detail. And so here we actually have a different kind of a dimple sheet that is providing a large path. You can get a bunch of different designs, but really once you're in the 1/4 inch to 1/2 inch range, you can pretty much put a small Niagara Falls vertically through this stuff. Take it to the perimeter drain. The perimeter drain becomes critical to be able to collect that water and drain the water away. So sometimes, and this is a very common question we get when we're working on higher performance buildings, is that, well, shouldn't we just waterproof it? And the short answer would be no. And the longer answer is waterproofing is a completely different animal than what many people think about it as. It's not a thicker membrane or a better membrane, because that's not that big a deal to do as we see here. You can just add a waterproofing membrane, but it's not waterproof because a waterproof system has to deal with a standing head of water, whether that's a 1 foot head or 1 meter head. It requires, therefore, that the wall be structurally designed for the possibility that you are resisting that standing head of water. So that means that you're now moving into a different world of below-grade parking garages in New York City, where you have 12 to 16-inch concrete foundations with double reinforcing, et cetera, to take that standing head of water. It also means you don't bother like waterproofing the wall to a head of 3 or 4 or 5 feet of water if you also haven't connected the floor slab. And so water will go from the soil, if it is actually 5 feet ahead, it'll actually push underneath and go up the floor underneath the slab. And in fact, one of my first work experiences while I was at the university doing co-op work terms was dealing with that oopsie, where someone had waterproofed the walls, had not waterproofed the floors. They finally got their first spring, they got water levels rising. The walls remained watertight and the floor slab lifted up and cracked and of course flooded the whole basement. So when you go waterproofing, it's like you kind of got to start at the slab and then work your way up the walls. And you need to be aware that if you succeed in waterproofing, you will need to be able to structurally resist it. Which is why for the vast majority of single-story below-grade basements in normal soil conditions, where the water table is more than a few feet below grade, drainage is the more reliable and the much more easy to execute and less expensive solution. So here's showing an image in the upper right corner of what waterproofing a slab would look like. There'd be a structural connection that's continuously waterproofed under the floor slab and everything. And there's a serious amount of structural work to be dealt with there. Marcus.
I'll just bring one question from the attendees up here briefly, John. That is, should we always use damp proofing and the drainage membrane over it? That was kind of alluding to your last slide, and you showed a slide earlier where you actually showed a doubled up version. That was damp proofing spray on the wall first and then the drainage membrand.
You try and go back to that actually.
There you go, that one.
Well, it depends.
Maybe let me briefly comment on it first from a building code perspective. I can share that what you see here in this picture is obviously compliant with code. You could also make this code compliant by only using the drainage membrane, but simply for the fact that in Canada, you need a CCMC approval for both functions. They're independent of each other. One requirement is drainage, the other requirement is damp proofing. And for the product shown in the picture, the product has an approval for both functions. So it will function both as a damp proofing as well as a drainage membrane. In the United States, there's only one requirement, and that only is with regards to the waterproofing. There's no requirement for drainage, and therefore, yes, the membrane can also fulfill that function or meets the intent of the code. But I think the person that asked this question, John, probably wanted to hear your opinion on what is preferable from your point of view.
Yeah, so I mean, I tried to make it clear that, you know, this is entry level. This is this is code in most jurisdictions, and code is a 4-letter word for the worst possible building you can build without going to jail. I'm saying that this is the step up I would do. So, you know, this is, if I were building my mother a house, this is the basement I would design for my mother's house. My mother-in-law, I would design this house, but my mother gets this house. And only when I have a special situation do I think to go to the next level up and have a filter fabric and a gap in you know, particularly wet, particularly demanding applications. So, you know, good, not good enough, good, better, best is sort of how I wanted to put it. And I wanted to say that occasionally you need waterproofing, but don't think of it as best, because in many cases it isn't best. It doesn't actually provide better performance. It may mislead people into believing it because they spend more money on a wall membrane, but you're not getting better performance. You're better off getting rid of the water than trying to do a really good job of waterproofing. And again, exactly like we approach walls. You're better off, if you can, draining the water away, reducing the pressure, than you are trying to stop it. All of this drainage is on having good perimeter drains. Just like a wall requires good flashings and weep holes, you can't make this basement drainage work unless you're draining it around the perimeter. And there's a lot of complexity. We could spend literally 30 minutes talking about the various ways to put in a drain tile. But a couple of points I mentioned here is, first of all, the drain tile should be above the floor that you're trying to keep dry. But below the floor. I mean, should never be above, should be below. You know, the more you can get it below, the better. You're trying to de-water the site. You're trying to reduce the water table level that might be here and bring it down underneath to where the footing is. So you need to try and make that happen. Figure out how to get the water to exit. Sometimes we have to pump it, which means that you're at the whim of the power supply and the pump working. Ideally, you want to drain that to daylight. And also, the reason for the crushed stone around the base of the wall is that it acts to collect the water in the soil more effectively and deliver it to the tile. And as well, in extreme cases, we know that it also acts like the drainage path itself, that it really acts like a French drain, which is basically crushed stone wrapped in a filter fabric like a giant burrito. The drain tile isn't the only thing that's draining water. So just let's summarize where we were with the basement below grade drainage stuff. Well, you definitely want to drain next to the wall so that hydrostatic pressure never pushes on that concrete wall. Ideally, you're doing that with a damp proof as well, but you can often just do it with a quality drain membrane. Then you have a perimeter drain, which is below the floor. And also don't forget to drain under the slab, because as I drew the water table coming down to the perimeter drain at the footing, well, it'll also go up as it goes towards the middle of the building. And so that's why we need to be able to have a good drain underneath the slab, which we'll come back to a little bit later on. Now, the other things that we have to deal with in basement wall designs is moisture from the inside. And because it's a basement, a building enclosure, we need to have an air barrier, we need to provide some thermal resistance, and we have to manage condensation, both in warm weather and in cold weather. And I mentioned here, beware of cool basements in climates that have cool, humid summers. So that may not be as important in Denver, but it certainly matters in Columbus, Ohio. It certainly matters in Lexington, Kentucky. It certainly matters in New York City, because the soil stays cool from the previous winter, and when it gets humid, that humid air will contact an interior surface that's connected to the soil, and then it'll get condensation. Now, a big choice to be made when you're doing a building of a basement is where you put the insulation. So this is a nice set of images from buildingscience.com. And you can either have the insulation on the inside, the outside, in the middle, or both the inside and the outside. Those are the practical solutions, believe it or not. All of those exist. Now, more likely, we're going to either talk about inside or outside. The one on the far right, both inside and outside, that's an ICF. I'll show a slide briefly on that. But the inside insulation is preferred by builders largely because of construction process issues. Putting the insulation on the outside means it has to be done early in the construction process, because you then have to do it just before you backfill. And it means that insulation routinely gets bashed up, etc. From a building science perspective, you'd much rather have the insulation on the outside. That's sort of the perfect wall concept. From a practical reality, most of our buildings are doing the insulation on the inside. And so building science community for 25, 30 years was pushing, no, on the outside. And over time, we've come up with solutions to how to do it effectively on the inside and meet the builder's demands that they need to do it later in the process and protect it from construction damage. So this is the exterior insulated type solution. This is an interior type solution. I'll describe a little bit more about these. And then this is an ICF, where there's both insulation on the inside and the outside. All of them, of course, have a drainage gap membrane that's provided. So as I mentioned, the below grade soil environment is always at 100% humidity, and you might have liquid water there. And depending on the season, the bottom of your basement wall in the wintertime is definitely much warmer than the top of your wall in the wintertime. And in the summer, the top is a lot warmer than the bottom. This is quite different than above grade walls, and it's actually quite confusing. It completely changes the moisture dynamics of how a basement works. It's different at the top than it is at the bottom. And the behavior in the winter is quite different than the above grade walls, and similarly in the summer. And so as a consequence, trying to follow the normal rules that one would use in below grade basement walls results in challenges. And also notice that there's a portion of pretty much every basement which is above grade. I've indicated that with the brace brackets above grade design. So you actually still have to design that part of the basement, that last 6 inches or so, and the rim joist and all that. That's all above grade wall design. And then you have this weird scenario down below. And this is where we get into trouble by just using standard sort of, vapor barrier, insulation, air water barrier, cladding approaches in basements. One of the challenges to vapor barriers on the inside is that they really cause problems in basements because there's lots of sources of moisture that are coming from the soil or wicking up from the footing, being fed into this space. And the shown here are, bags of insulation with a plastic facer, just disastrous in almost every climate zone where people build basements, like zone 4 and north. The best sort of generic new build basement solution that manages moisture from the outside and the inside, I'm showing here. This works in pretty much all situations. It allows you to get to very high insulation levels if desired, but by having a continuous insulation up against the concrete foundation, but that insulation is airtight and vapor resistant, it separates the indoor humid air in the summer from the cold concrete. In the summertime, it also stops water from the concrete diffusing into the building. The wood framing and fibrous insulation allows you the opportunity to get a lot more R value at low cost and provide a service space. But of course, that perimeter drain has to be there. The drainage gap membrane and drainage plane damp proofing has to be there to manage the outdoor liquid water. And then, of course, there's also insulation below the slab, which I'll explain why that's important. So this is what that kind of looks like. The image on the bottom left is showing you the continuity you can easily achieve with the floor slab insulation and air vapor barrier with the concrete wall. And you can actually see this as a continuous broken insulation layer. And here the studs are sitting there ready to go that you can put wiring in, plumbing in, fibrous insulation. And this is a moisture safe. Just don't put a vapor barrier on it. This is a moisture safe system. Another increasingly popular system for basements, at least in high performance, higher demanding environments, are ICFs, insulated concrete forms. For those of you who don't have all the jargon of the acronyms down, it needs a drainage match as much as the other walls do. It's not magic. The concrete in these things also cracks. Yes, the insulation on the outside helps, but it's not good enough. Not good enough to rely on yet. So it's pretty easy to put a drainage mat on. Again, I would argue that the drainage mat here would be more effective than using a peel and stick membrane in terms of managing water. And you can see the insulation underneath the slab. We often have to retrofit walls in the basement situation. Older walls, whether rubble masonry or brick masonry, stone masonry, And these types of older walls, often when we get to this building that might be 100 years old, you know, you go in the basement, it's pretty obvious it leaks, and you can do that by an obvious visual inspection. And so one of the options would be, well, let's just dig up around the whole building and put on some damp proofing and add a drainage gap. But that's so impractical in so many situations. There's historic significance, there's neighbors, there's sidewalks, there's decks, there's front stoops. Sometimes there's just prize rose bushes that we're not allowed to dig up from the outside. And so the alternative is you can put the drainage on the inside. One of the easiest, most effective ways to do that is to use a dimple sheet. But that drainage gap has to be air and vapor separated from the inside. So you put up the dimple sheet, preferably taped and sealed, and then you put insulation on the inside. Another technique is put up the dimple sheet and use spray foam on the inside. And that gives you your thermal and your air and your so on tightness. And the dimple sheets provide drainage. Now, you still need that base perimeter drainage detail, as I've shown in this drawing here. You're digging out a trench, you're putting in a tile, you're leading it to a sump that either goes by gravity or electric pump. Here's some images. Actually, the bottom right image is a photograph from Joe Stiebrick's house, actually, which is 150, 60 years old, and that's how they were dealing with the drainage on the inside. Here they're putting in a whole floor slab. That's why the insulation bucket is down there. On the upper left, that's just a normal retrofit situation where we've chipped out a foot of concrete. The dimple sheet is being carried down to a drain tile. And this is what they look like when you spray foam. The bottom left is actually a residential in Boston. A commercial system where in that basement, things of high commercial value will be placed, and they did not want to risk moisture damage either from summertime humidity or from leaks, from floods, and so on. And so that's why that technique was chosen. So I thought I'd end up with the last bit on below grade slabs. And in slabs, the moisture is probably more often from humidity above condensing on cold slabs, especially in somewhere around May and June. It gets warm outside, you get those warm days, everyone's happy, except the slab is still cold from last winter. It has a long memory. And so what we need to do is manage the temperature of that slab so it doesn't allow condensation. Ideally, you're insulating that slab. And then you're stopping water from wicking up from the wet soil or diffusing up. And that means a capillary break or a vapor barrier. In addition, increasing jurisdictions are demanding, and good practice suggests you should air seal that floor slab as best you can. They're demanding it in various jurisdictions because of the radon problem. But it's not a bad idea to air seal penetrations, and in particular, that wall to slab detail quite carefully. And I think more and more we're going to be demanding that you do that. So keep the slab warm, block vapor and capillary flows of water from below, and seal against soil gases. That's the basement slab solution. And this is a pretty reasonable solution. I mean, there's not a lot of variations that are perform as well and make any sense than this assembly. A concrete slab on a vapor and radon air barrier, on insulation, on some sort of clear drainage layer made of stone or drainage mat. You can use the foam as the air barrier and the vapor retarder. It's not as great a vapor barrier, but it's not bad. It's usually more than sufficient. But if you're going to use the foam, you need to tape the joints because that really, this really works. You see them taping around the posts, etc. So it's an effective air and radon barrier. Again, retrofit. We have to go back and upgrade buildings that we've already built. Using dimple sheets as a very effective vapor and capillary break barrier and some insulation is one cost-effective, low-thickness solution. If you don't have a lot of headroom, this is probably the best you can do. If you have higher thermal aspirations and you have lots of headroom, you can also put insulation down on top of that slab. But again, vapor, you got to make it airtight, and you got to use insulation that has good vapor resistance. This is a solution. This is actually in Waterloo, installing a dimple sheet, sealing the joints between to make it air and watertight. One of the challenges between pre-manufactured slabs is that they have lots of joints which are difficult to seal. So they don't quite fulfill the function. They work on keeping the liquid water from wicking up and water vapor from getting too much into the wood on top, but the joints are not really a solved problem this way. So this is just a couple slides of images of what that floor solution looks like before I wrap up here. So you got to manage the water below grade, above grade as much as possible. Solve a lot of your problems. Drain the water below grade next to walls and below slabs. Perimeter drainage pipes, air gap membranes are very powerful and effective solutions. And then you need to design your assemblies to avoid condensation or manage condensation by keeping moisture-sensitive surfaces warm. And I just want to let people know that there is an upcoming guide. It's not quite published yet, unfortunately, in its final reviews, that BC Housing will be releasing. That a lot of the images I presented in this presentation come from that. And there's a lot more detail about challenging site conditions and how to manage water. So hopefully we have some time for more Q&A. Marcus might have some closing words and other things to share with us.
Yes, well, first of all, thank you very much, John, for the presentation, for this webinar, for your explanations, and sharing your insights. There is one repetitive question that I'll answer first. That is, can we have the slides or can we get a recording? So may have been some attendees that joined us later. So I'll repeat that again. Yes, we recorded this webinar and we will make the recording available to everyone who signed up today. So John, there are a number of questions. So I guess we can take a few minutes to try and touch on some of them, and perhaps you can try and flip back to the respective slide. There is one here, for instance, that says, in the retrofit masonry wall detail, won't trapping of moisture in the wall saturate and threaten integrity of wall and conceal condition of that old foundation wall?
Short answer to that is not really, because that wall has been soaking wet for its entire life before I got there. And so it's wet to the touch. When you go there, you walk up to the wall and you can feel it's damp. And so masonry and mortar, they don't mind being wet. There is a point to be said about if you have lots of liquid water flowing through a wall, the older walls with lime, you can dissolve the lime over time and wash it away. But that's a judgment call to make when you're inspecting the are you getting so much water drainage through that you're washing the lime away and have to solve that problem? So true, but the vast majority of these older masonry walls, they've been wet their entire life, and they're not going to be made really any wetter than what they are. It's just the wetness is not connected to the indoors anymore.
Very good, thank you. Here's another question. How important is capillary break on top of footing? Can a simple thorough seal brush on product suffice? I've had issues with membranes conflicting with rebar dowels.
Yes, so how important is it? It depends on how you design your wall. If I'm looking at this wall or this wall, so the ICF wall, or as long as there's foam layer on the inside, that water wicks up the footing into the concrete wall, isn't the end of the world. However, in a lot of situations where, for example, all insulation on the outside, it's a big deal. It's an important issue to deal with. How do I avoid water wicking up that footing, as is being shown here on the right-hand side image? That can be a big deal. And so does it work? Can you put Thoroseal on the top of the footing? Well, I don't know about Thoroseal being the right choice, but you could probably get a number of brush-on vapor barrier products, and we played with a lot. One of the challenges with them is that those brush-on products require the concrete to be dried. I know, it's surprising, I understand. And so we got pushback on that front from builders, and also it took curing time, and so it was sticky. And builders who work in basements are particularly sensitive about stickiness. I don't know, that's just what they complain about. And so there are products where you can get a capillary break on a roll that you roll out on, literally on the damp, wet concrete, not even damp, wet concrete, and you trowel it into the concrete. It's got fuzziness to it. Yeah, you have to cut holes around it for the dowels, but it's not really a big deal. In fact, put the dowel in after the membrane. So you can get membrane products, which are like completely perfect vapor capillary breaks, I mean. And so that is sort of the best option when you need a capillary break.
Very good, thank you. There's one more here I'd like to bring up, and that is, can you give an example of a Zone 4 below grade foundation that you would consider ideal?
So I think that this is an ideal below grade Zone 4 basement system. And I'm not sure whether we're talking, Southern Ohio here or where, but I mean, has a drainage gap, uses a concrete foundation, not CMU, tends to be stronger and more reliable. Continuous layer of insulation you see up against the wall, the concrete wall, 2x4, 2x3 on the inside to run services, put up your drywall and all the rest, meets all the fire codes. The only thing really that's a little weird about it is that I'm showing closed cell high density insulation at the rim joist, and that's just because of the air tightness challenges in that complex framing zone. But that is a fantastic approach to a Zone 4 basement, and you can dial this insulation value up to passive house levels if you want, or dial it down to code minimum if that's what you want.
Very good. And I'll bring up one last question here for the moment. That is, if somebody insulates the foundation on the outside, on the exterior side, would you then put a dimpled membrane or drain board inboard of the insulation or outboard of the insulation?
Well, that's an interesting, not surprising question. The answer to it is yes. So you have options. And I guess the thing to talk about, though, is that if I put the drain board behind the insulation, people are not wrongly concerned, hey, well, doesn't that short circuit my insulation? And the short answer to that is no. All those details we talked about in terms of sealing the top edge, where you have like a profile and put caulking in there and the gap is only this big, means that you do that, no impact on the thermal performance. So you can put it on the concrete. And that is where most of the dimple sheets install best. People are most comfortable installing them there. And you don't lose performance in the insulation than putting the insulation on the outside. That said, I know several builders locally that I've worked with for 20 years that actually do like putting the dimple sheet on the outside of their insulation. So they put on a damp proofing on the concrete foundation. They put up a couple inches or now more of extruded, and they put the dimple sheet on the outside of that. And that does work. So both can work.
Excellent. Thank you very much, John. I want to thank you again for this webinar, for sharing your presentation. We are pretty much out of time. There are more questions, but we will try and respond to them collectively in one document and send it out to all participants in the coming days.
And next week we have some, you have some special guests from afar.
Yes, there's more coming up. Exactly. I have a slide coming on that here. Let me just quickly wrap up. Basically, some of the dimpled solutions or drain boards that John touched on, that is what we as the Dorken company do. We have been manufacturing such products for over 40 years now. And our most common product for residential foundations is the one we see here. It's very recognizable in chocolate brown with an orange stripe on it. The function was sufficiently explained by John. It spans cracks, it provides a drainage gap so that water that may enter into that gap can freely flow away and downwards to the drainage tile. What makes us special, or what makes this product special, is that we waffle recycled polyethylene in the middle and encapsulate that between virgin layers. Why is that important? Well, first of all, we do want to be green, and we want to use recycled material to help protect our planet as well. But at the same time, recycled material is more susceptible to stress cracking, to damage, to degradation over time. With virgin material, we can control that better. And that's why we co-extrude our material. So you have recycled in the middle, encapsulated by virgin on the outside. That's the only product that's in the market that is made this way. We obviously have a range of accessories as well. We have fasteners, we have cap pieces, we have sealants. You see on the lower left side what we call a screw fastener that becomes relevant when one wants to first install the insulation on the foundation wall and then the drainage board. So this is a fastener that simply tightens into or fastens into the extruded insulation board. And our product has been used on many, many thousands and thousands of foundations in North America, also in Europe, and it has a lot of history and experience. We have a lot of history and experience in that field. Lots of technical resources. If you're interested to learn more about us, we have tons of installation videos, installation guides, accessory lineups. We have all kinds of building code approvals, both in Canada and the United States. And most of all, or most important of all, we have a certified installer program, which means that we're working with people that we train, factory train, and that know very well all the things that John talked about this afternoon, understand the importance of details, of installation details, and that's what they can execute on foundation walls. So if you're interested in learning more, please come to our website, dorken.com. You'll find a lot of information there, and also good ways on how to contact us. And with that being said, we'd like to point out there is, what John touched on already, another webinar coming up next Friday, May the 8th at 1 p.m. Eastern Time. It's called the Building Science Advisor. That's a software tool. John, you're familiar with this tool?
Yeah, so we've been one of the people that they've asked to review it and asked for ideas. So it's been in the works for several years, and they're really at the point where it's useful and being rolled out.
So this tool has been generated by Oak Ridge National Lab, a large lab, government funded in the United States. Andre Desjardins heads the Building Science Department at Oak Ridge National Lab. And he is one of the key drivers behind this project here. Building Science Advisor, a software tool where builders can basically go in, check by climate zone or by location where they're building, and then basically select from different building components to verify, does this work in my area or not? Or does this type of building or wall assembly work in my area or not? Do I have to anticipate any issues with moisture? And does it comply with code and so on? So it will be a very informative 1-hour webinar as well, presented by Philippe Baudreau and by Andre Desjardins. We also have an upcoming video feature with John, which is very exciting. This is a 7-minute test hut tour that has us joining John on his way into his backyard and giving us a tour of a natural exposure test facility there. And with that, I'd like to say thank you again. Thank you to John. Thank you to all those who have attended. We hope you enjoyed it. And we look forward to seeing you next time. And in the meantime, please be safe. Thank you.
Bye all.